All right, everybody, we're about to start the third chemistry lesson. This time I actually also have my camera on, so you'll see me as I teach because I will need to demonstrate some stuff on the whiteboard that I have behind me right here. I have a couple things I need to demonstrate. But so let's go ahead and get started. I'll open up the PowerPoint here. So energy. The simple way of describing energy is the ability to do work. Energy is a word that's easy to understand, but it's really hard to describe. I've heard it explained that energy is a bit like wealth. So it's hard to describe wealth because think about it. If you say somebody's wealthy, what does that mean? That could mean a lot of things because you could not have a single dollar but be wealthy because you own a lot of property or because you own a lot of expensive objects, right? So, and you can take, if you have wealth in the form of a lot of money, you can then spend all that money and buy a lot of stuff. You're still wealthy if you own a ton of homes, even if you don't have a single dollar now. Your wealth could all be stored up in the bank. It could be in cash. Somebody could be wealthy because they have all their money locked up in some retirement account they can't access for the next 20 years. It's no good to them right now, but they're still wealthy. You see, so energy is like that. It's the ability to do work, and energy can move around into all these different forms. That's what makes it so hard to define. So you could have kinetic energy, which is the energy of motion, like I'm using kinetic energy when I wave my hand. Potential energy is the energy of position, or basically it's the ability to turn something into kinetic energy. So like right now, this pen is right here. The higher I lift it, the more ability it has to fall and travel at a faster speed when I let go of it. Thermal energy is the energy of random particles as they move in random direction. When people think of thermal, they think of heat. And if you didn't know this, what actually causes the heat in any object is that its particles are moving faster. So right now I actually have a cup of hot water. You can kind of see the steam coming out. This is hot water because all the particles are moving in a random direction. Whereas right here I have a water bottle. This is cold. Well, it's still kind of cold. Same exact kind of water. These are moving very slow. The particles in the hot cup of water are moving fast. That's what creates heat. That's what makes something feel like it's warm, is that its particles are moving faster. Electrical energy comes from, it's the type of force that moves electrically charged particles. Chemical energy is the energy that's released when bonds break. And the nuclear energy is the energy released when particles are added or taken away from the nucleus. All right, so today we're going to cover 3 laws of thermodynamics. So thermodynamics is the science that studies movement and conservation of energy, especially thermal energy. In fact, you know what? Before I get into the first law of thermodynamics, go ahead and answer question number 1. Question number 1 says, what is the difference between kinetic and potential energy? Go ahead and answer that in your best definition. So pause it, answer that, and then press play and we'll move on. Okay, so your answer for that, a lot of answers could work for that. Kinetic is energy when stuff's actually moving. Potential is when it could move. You could put energy of motion, energy of position, anything like that. Okay, so now the first law of thermodynamics. They also call it the law of conservation of mass energy. You probably heard this before. It's simply this idea that matter and energy can be neither created nor destroyed, only converted from one form to another. So what that means is that when you grow, you eat something and you begin to grow. It's not that you destroyed the hamburger and then your body grew larger. That's not what happened. What happened is some of the matter that was in that hamburger gets transferred to your body. So it's really weird to think about that, though. If we say here that matter isn't being created or destroyed, it's just converted from one form to another, it's really weird to think that all the particles that make up your body, you didn't make those particles. Okay, you've arranged them into your body, but the particles that make up your body were there before you. It's really weird to think about it. So like the different atoms that are making up my hand, who knows what they were 100 years ago? They weren't me. They were out there doing something else. It's so crazy to think about this. The particles in your hand, I mean, some of them might have been an asteroid at one point. Some of them might have been, I don't know, an elephant. They could have been water floating around in the ocean. They could have been in some mountain. And these particles have just been moving, and now you're holding on to them. It's just a really weird way to think about things. But so matter and energy isn't getting created or destroyed. It's just converting from one form to another. So think about there's a lot of energy, chemical energy in the gasoline in your car. So what's going to happen is when that car turns on, all that potential energy and chemical energy, some of it is going to be acoustic energy to make noise. Some of it is going to be thermal energy to warm up the engine. So some of it's going to be kinetic energy to move the car. So if however amount of energy there was in that gas, if there was joules, we'll get to this later, but joules is how you measure energy. If there was 100 joules of energy, then 100 joules of energy is going to be used when it starts. So the idea here is that energy and matter isn't getting created or destroyed. It's just moving from one form to another. And then the second law of thermodynamics is this idea. I want you to imagine, let's go back to it. If you drop food coloring into a beaker of water, does it stay as a little droplet as it travels down? No. You drop something colored into some water, and it disperses all over the place. This is because of an idea called entropy. And what entropy says, so the second law of thermodynamics is this idea that all processes tend towards highest entropy. It's why the food coloring, the little particles disperse, because they are tending towards higher entropy. Entropy, a simple way to think about it, is just the measure of disorder or randomness. So the second law of thermodynamics just says that all natural processes tend towards highest entropy, meaning if stuff is left, it gets chaotic and disorganized. Things don't stay in neat rows. They fall apart, right? So that's why it takes energy to, well, think about like if we have a nice building. If we just leave it, does it stay a nice building forever? No, that thing begins to fall apart and it begins to crumble. Any object, if left for long enough, it starts to just fall apart and crumble. So that's the idea of the second law of thermodynamics. So go ahead and take this time, answer the next two questions, summarize the first two laws of thermodynamics, press pause, go ahead and summarize those. I'm not going to go over these after you press play. You see them right here on the slides. Go ahead and summarize those before we move on. Press pause when you're done with those, then we will move on. All right, so we'll move on to past the second law of thermodynamics to thermal energy, temperature, and heat. All right, there's a difference between all three of these concepts. So basically, there's all the evidence in the world points towards the idea that all the particles in matter are constantly moving. Another thing that's weird to think about, like right now, if I just hold totally still, I'm not still because all the little particles that make me up, they are moving. Now, that's such small movements, we can't see them, but they're all moving. And so if you take the energy of the movement of all the particles inside of an object and you add up the energy of their movement, that's called kinetic energy. Okay, so the kinetic energy is all of the movement going on inside of you. So there's three different things. I want you to understand the difference. So let's take something hot, like this cup right here. I boiled this water right before I started this. So then you can see the steam. It's like it hurts to even touch. This is burning hot water right here. All right. So the temperature of this water is really, really high. I mean, it just boiled. So that's 100 degrees Celsius, 212 degrees Fahrenheit. It's been cooling off for a second. So this is probably still 180, 190 degree water right here. Really hot. I don't want to touch it. Okay. Temperature of the water is high. What temperature does is it's the average kinetic energy of each particle. So each particle in here is moving really fast. So the temperature is saying each particle has high kinetic energy. Thermal energy is the total kinetic energy. All right. So this cup full of hot water has each little particle has a high temperature because each particle has a lot of energy, but one particle by itself can't do much. The fact there's a lot of particles in here and they all have high energy means this thing as a whole has high thermal energy. All right, so basically, temperature is the average energy. Thermal energy is the total energy. Okay, so I'm going to give you a demonstration. Look, if I was to put my finger in here, it would hurt really, really bad because it's burning hot. What I'm going to do is I'm going to take this little thing. I'm going to pour out a little bit of water. Okay, so see, I've got some water in here now. Let's do this. So I've got some water in here now. And what I'm going to do, so the temperature of the water in the cup, really high. The temperature of the water in this little dropper, really high. Both of them have the same temperature. But watch what I'm going to do. I'm going to take this burning hot water, and I'm going to squeeze out just one drop onto my hand. I'm trying to be careful. I don't want to squirt it all. That would actually hurt. So I'm going to squirt out just one drop. There we go. That was a few drops, but that didn't hurt. So a few drops on my hand, that didn't hurt. That was fine. And this burning water right here. So if I stick my finger in there, it's going to hurt. If I just do a few drops, it doesn't hurt. They both have the same temperature. The whole cup has a high temperature. Each little drop has a high temperature. Temperature isn't what hurts you. Thermal energy is what hurts you. Here's the thing. Temperature is saying each little droplet has a lot of energy. But the total energy they can muster up, if it's just one or two drops like you saw on my hand, that's not enough thermal energy to hurt me. If I dump this whole cup out on my hand, that's more than enough thermal energy. So see, temperature isn't what hurts you, it's thermal energy. And then lastly, heat. I didn't feel any heat on my hand because there wasn't a sense of temperature change. So one or two little droplets is not enough to change the temperature of my hand. That's why I didn't feel any heat. So just make sure you understand in terms of temperature, thermal energy, and heat, why doesn't a small drop hurt your hand? A small drop of boiling water, how come that doesn't hurt your hand when the whole bucket would? It's because the small droplet has just as high temperature as the bucket. The difference is that you have to have a lot of water to create enough thermal energy to actually hurt you. And then what happens if you transfer thermal energy from one object to another? It's called heat transfer. Now, this is kind of like one of those kind of interesting facts that you just like, I don't know, you can try to act smart by telling people this kind of thing. Thermal energy always flows from a higher temperature to lower temperature. So here's what you can tell your mom. When in the middle of the summer, when it's burning hot outside, if you leave the front door open, what do your parents get on you about? What's your mom going to yell at you about? She's going to say, hey, you're letting the cold air out. But look at this. Thermal energy always flows from high temperature to low temperature. So when mom says you're letting the cold air out, is mom wrong or is she right? She's wrong when she says that. Because look, thermal flows from high temperature to low temperature. So if she says you're letting the cold air out, you can go, no, mom, I'm letting the hot air in. Because energy always flows from high to low. So it's just one of those, you'll probably get in trouble for that. In fact, here's another thing you could use. If your room is really messy and your mom goes, hey, how'd your room get so messy? You can just say, mom, it's the second law of thermodynamics. All processes tend towards highest entropy, which is disorder or randomness. You can drop that one on her too. All right, so let's do this. Go ahead and answer number 4. Press pause, answer number 4, and then press play, and I'll go over it, make sure you got it right. All right, so the drop of water doesn't hurt my hand because even though it has high what? Each little droplet and all of the water, they all have high temperature. So they have high temperature. Even though it has high temperature, it has low thermal energy. So it has high temperature, meaning each little particle has plenty of energy, but it's low thermal energy. It's not enough particles to make a total energy that actually hurts me. All right, moving along. Exothermic and endothermic. So exothermic is when you have a chemical change that releases energy. and endothermic is a chemical change that absorbs energy. So if you start with a lot of energy, you go through reaction, you have less energy, boom, you released energy. Probably the stuff around you is going to be hot, but you've cooled down if that's what happens. Endothermic is going to absorb energy. So it's going to be sucking in heat from the stuff around it. So it's going to gain energy as the process goes on. So go ahead and answer these questions right here. Number 5. A reaction takes place. This is what we'll do. Go ahead and pause, answer number 5, and then press play, and I'll go over with you. Okay, so a reaction takes place. After the reaction, the system has more energy than before the reaction. It must be what? What is it if it's absorbing energy? Endothermic. Think N kind of sounds like in. Energy goes into it. Exo, exit. Energy is leaving. So now we are actually going to do a little bit of math for the last few questions. That's why I have this camera running so I can demonstrate on the whiteboard behind me. So we have the Celsius, the Kelvin, and the Fahrenheit scale. The Celsius scale, the whole point of Celsius is 2 points of reference. 100 degrees Celsius is where water boils. 0 degrees Celsius is where water freezes. That's the whole point of Celsius. Kelvin is a different scale. Kelvin is a scale where everything in Kelvin is positive. There's no such thing as negative degrees Kelvin. So what Kelvin does is it takes the lowest possible temperature, the lowest energy you could possibly have, and that's 0 degrees. Okay? 0 degrees Celsius just means water freezes. You can go way below 0 degrees Celsius. Kelvin takes that and shifts it up. So 0 Kelvin, 0 Celsius would be way up here. Water freezes. 0 Kelvin is way down here. At 0 Kelvin, all movement stops. And we call that absolute zero. Now, absolute zero is not even a real thing. It's not possible in the real world. And the reason is, remember this idea up here, that when I explained that energy flows from high to low. So what that means is if, say, I was able to get, say, my pinky to be 0 degrees Kelvin, I got it to be absolute zero. Well, if anything else in my hand has any amount of energy, it's going to flow over here and take this thing that was at 0 and move it up above 0. Okay, does that make sense? That anywhere, you can't have absolute zero anywhere in the universe, because any place with 0 energy, the energy around it is going to flow to it and balance it out. So there is this TV show called The Flash. I watched like a couple episodes, couldn't get into it. I've been told I need to stick with it. It gets better as you go. But I remember in one of the episodes, they had this freeze gun where the inside the gun they said was absolute zero. And so they open it and it freezes everything around it. That's impossible, because if the inside is absolute zero, it's going to be sucking in any energy in the gun itself. Any heat is going to go in there to make it go above absolute zero. So like it doesn't work. But anyways, so that's what Kelvin is. Basically, so Celsius, 0 water freezes, 100 water boils. And then Kelvin is the same as Celsius, except for it's 273.15 degrees higher. So you take whatever the temperature is in Celsius and go up by 273.15, and that's what your Kelvin scale is. So that's why if Celsius is at negative 273, that we call it 0 Kelvin. That's where all movement stops. So basically, to convert from Celsius to Kelvin, you take whatever your temperature is in Kelvin, if that's what you're trying to find, and just take Celsius and add 273. If you want to know what it is in Celsius, just take the Kelvin and subtract 273. So I'm going to write some formulas here that might be helpful. I would suggest jotting these down. So if you want to go temperature in Celsius to temperature in Kelvin. So you want to go from Celsius to Kelvin. What you do is your temperature in Kelvin will just equal whatever the Celsius is So for Kelvin, just take whatever the Celsius is and add 273.15. If you want to go from temperature in Kelvin to temperature in Celsius, just take whatever the Celsius is. Take whatever the Kelvin is and subtract 273.15. Okay. That's all we need to do for that. So if I have 100 degrees Kelvin, what will that be in Celsius? And then let's go from 100 degrees Celsius and go to Kelvin. Let's go back and forth. So my example, if I have 100 degrees, let's see, the first example wanted me to do, if I have 100 degrees in Kelvin. So if I have 100 degrees Kelvin, then how many degrees do I have in Celsius? So look at what you do. If you want Celsius, just take whatever the Kelvin is and go minus 273. So for this, just take the Kelvin and go minus 273.15. And when we do that, our answer is just negative 173.15. I will be okay with you using calculators in this class. If you're coming from Casino's class last year, he doesn't like letting you guys use calculators. I will let you use calculators. There's a ton of just crazy decimal math in chemistry where you're going to want a calculator. Number 2, now we're at 100 degrees Celsius. Let's turn that into Kelvin. So take 100 degrees Celsius and add 273.15. And so we'll get 373.15 degrees. There we go. All right, so that is how we move from Kelvin to Celsius and from Celsius to Kelvin. Okay. It's not too bad. You just add or subtract 273, and that's all you need to do for that. And we would be totally done. That's it for the math if it weren't for the stupid stuff that we have in America. We have the Fahrenheit scale. Everybody else is happy with Celsius. It's very simple. It has good reference points. At 0 degrees, water freezes. At 100 degrees, it boils. Instead, we have to deal with the system that we have, which is Fahrenheit. So to go from Celsius to Fahrenheit, you take whatever the temperature in Celsius is, you multiply it by 1.82, and then you add 32. So here's how it is. If you want to know your temperature in Fahrenheit, you have to, take 1.8, multiply it by the temperature in Celsius, and then add 32. Kind of stinks. If you want to go backwards, if you want to figure out your temperature in Celsius, then what you need to do is you need to take the temperature in Fahrenheit, and then what you need to do, you need to subtract 32, and then divide the whole thing by 1.8. So those are the formulas we have to use. So if we're doing something like this, where water freezes at 0 degrees Celsius and it boils at 100 degrees Celsius, convert both of those to Fahrenheit. So let's go ahead and do that. So we got to figure out 0 degrees Celsius, and we need to figure out 100 degrees Celsius and turn them both into Fahrenheit. So look at the formula. If you want to get Fahrenheit, do 1.8 times your temperature in Celsius plus 32. So right here, to find it in Celsius, we'll do temperature in Fahrenheit equals 1.8 times the 0 degrees Celsius plus 32. Temperature in Fahrenheit equals 1.8 times 0 is 0 plus 32. My final answer is 32 degrees. So water is going to freeze at 0 degrees Celsius, which is the same as 32 degrees Fahrenheit. You might have recognized that. It freezes at 32 degrees Fahrenheit. Water will also boil at 100 degrees Celsius. Let's figure out what that is in Fahrenheit. So temperature in Fahrenheit equals 1.8 times 100 degrees Celsius plus 32. So what we'll get here is 180 plus 32. Temperature in Fahrenheit is going to be 212 degrees Fahrenheit. That's our answer. So what's easier to remember, that water boils at 100 or at 212? I think it'd be way easier to remember it boils at 100. I wish we used Celsius scale, but for whatever reason, we have to use Fahrenheit. So let me minimize this. So I want you guys to do these problems. Let's go ahead and try to do 6, 7, 8, and 9. Pause this, give those your best try, and then I will go over them with you. All right, let's go through these. I think what I'll do is I will put the formulas back up here while we work. So we have temperature in Kelvin equals temperature in Celsius plus 273.15. Temperature in Celsius equals temperature in Kelvin minus 273.15. Temperature in Fahrenheit equals temperature equals 1.8 times temperature in Celsius plus 32. And then temperature in Celsius equals the temperature in Fahrenheit minus 32 divided by 1.8. Okay, so those are our formulas that we'll be using here. So the first question, it's going to be, the temperature is 50 degrees Celsius. What will it be in Kelvin? So we're going to do this one right here for our first question. We know what it is in Celsius. Let's turn it into Kelvin. So the temperature is 50 degrees Celsius. Let's make it into Kelvin. So you find temperature in Kelvin. This is number 6. Is going to be whatever it is in Celsius, which the question for 6, it's 50 Celsius. So 50 Celsius plus 273.15. Okay, that's all we have to do for that. So you'll find, I think you'll prefer going from Celsius to Kelvin and Kelvin to Celsius. When you're not going to like it is when we have to start doing Fahrenheit. That's what gets kind of tough. Trying to move this so that you can see the whole thing I'm doing. All right, so temperature in Kelvin will be, that would be 223.15. Okay, number 7, it's 300 degrees Kelvin. So now we'll do temperature in Celsius equals 300 degrees Kelvin. Since it's Kelvin, you do minus 273.15 to go from Kelvin into Celsius. And so our temperature in Celsius, that will be 26.85 degrees. Okay. Number 8, the temperature is 50 degrees Celsius. So for number 8, it's 50 degrees in Celsius, and we need to turn it into Fahrenheit. So we'll go temperature in Fahrenheit equals 1.8 times 50 plus 32. So that will give us 1.8 times 50. That could be 90. Yep. It'll be 90 plus 32. And so 90 plus 32 gives us 122 degrees Fahrenheit. And then last problem you have on there, number 9, is the temperature is 50 degrees Fahrenheit. What will it be in Celsius? So we use this right here where you know what it is in Fahrenheit. You need to turn it into Celsius. So temperature Celsius will be whatever it is in Fahrenheit, which is 50. So it's going to be 50 minus 32 over 1.8. And so temperature in Celsius we have 50 minus 32, which will be 18 over 1.8, and 18 divided by 1.8. Our temperature in Celsius here will be 10 degrees Celsius. Okay, so that's an example of using each of those to do each type of conversion. So at this point, I expect that you now can convert from Celsius to Fahrenheit, Fahrenheit to Celsius, Celsius to Kelvin, and Kelvin to Celsius. With that, we get to our very last question, number 10, and here's the answer number 10. The third law of thermodynamics. And I explained this earlier, but the third law of thermodynamics is simply put this, that the absolute zero is impossible. It cannot happen in the real universe. You can never have absolute zero. Therefore, 0 degrees Kelvin is an idea, but it's not a possibility. It's not a reality. So that's the final law of thermodynamics. So your laws of thermodynamics, you have that matter and energy can never be created or destroyed, only converted from one form to another. That's number one. You have number two, the law of entropy, that all processes are tending towards highest entropy. And number three, that 0 degrees Kelvin is not possible. So there's the laws of thermodynamics. Those are basically the laws of energy that nothing we know of in the universe will violate. And that is it. So it is a Friday today, so I will be available for tutoring from 2 to 3. If, however, you have questions before that, you can always email me and ask me questions, and I'll be available all day to help you guys. So I hope you have a good day, and I will see you guys next week.